Over 466 million people suffer from deafness or some other serious hearing impairments. Most of these people have communication difficulties that prevent them from fitting into society. That can affect the deaf in many ways. That can cause social withdrawal, loneliness, isolation, or even frustration. Symptoms like mental and emotional issues, a drop in self esteem, or lack of confidence can be common between all of them. And sometimes it can get even worse due to the potential failure in school and the increasing rates of unemployment. All of these are just a small sample of their suffering and pain, and even though there are some solutions for them to fit in between the others, there are still many problems to solve. Due to the great breakthroughs in AI and the rapidly growing technology, it's obvious that we can find many solutions for the deaf using the power of AI. In a nutshell, AI or artificial intelligence is the simulation of natural intelligence in machines. These machines can be programmed to learn and mimic the actions of humans, to gain artificial experiences, and to perform human-like tasks with human-like performance. So, inspired by this great evolution, we propose an approach empowered by AI and deep learning to help the deaf. Our proposed project mainly consists of two subsystems. The first subsystem utilizes the huge progress in the fields of computer vision, like object detection, pose estimation, optical flow extraction, and human activity recognition to build a sign language translation system. That system translates the sign language from video to text. Our translation system can operate either as a word-level sign language recognizer that outputs one word at a time, or as a sentence-level translator that can generate full sentences using a language model. In the second subsystem, we take advantage of the current advancements in the fields of natural language processing like speech recognition that will allow us to have an automatic speech recognizer that has the ability to convert the spoken language into text to help the deaf understand the people around them.
We use two main datasets, one for sign language recognition and another for sentence level translation. First, word level American Sign Language video dataset. It contains more than 2000 words performed by over 100 signers, with videos of lengths ranging from 0.36 to 8.12 seconds, and the average length of all videos is 2.41 seconds. Based on this large-scale dataset, we are able to experiment with several deep learning methods for word-level sign recognition and also evaluate their performance in large-scale scenarios. There are four subsets of the dataset as indicated by the table. They acquired 21,083 video samples with a duration of around 14 hours in total, and each gloss has 10.5 samples on average, which is almost 3 times larger than the existing large-scale dataset Boston ASLLVD. Second, RWTH Phoenix Weather Dataset, which is a large-scale real-life continuous sign language recognition and translation benchmark dataset that feature professional interpreters recorded from the daily news and weather forecast of the German public TV station Phoenix. It covers continuous German Sign Language with a vocabulary of over 1,000 signs, about 9 hours of training data. It contains 60,841 videos by 9 signers, and all the recorded videos are at 25 frames per second, and the size of the frame is 210 by 260 pixels, and each frame shows only the interpreter box. As such, this corpus allows to train end-to-end sign language translation systems, from sign language video input to spoken language. After reading several papers, we reached to several approaches, which we think it produces the best results on the datasets. Let's talk about the first task, the word-level sign language recognition. In this task, we take several approaches to convert the video to text. We detected the 2D key points of Synar's body from the input RGB frames as indicated. We created this video using a pose estimation state-of-the-art model OpenPose from CMU University. Then these key points are passed to a graph neural network to exploit the spatial relationships of our key points. Then pass its output to an average pooling layer to compress it over the spatial dimension. Then propagate our feature maps through a transformer encoder to process the temporal information.
In the second approach, we use a pre-processing method to extract the pattern of apparent motion of objects between the consecutive RGB frames. And to achieve that, we use an end-to-end deep learning model called Recurrent or Pairs Field Transforms for Optical Flow, or for short, RAFT. RAFT is a new deep network architecture for optical flow that achieves state-of-the-art performance with strong cross-dataset generalization as well as high efficiency in inference time and parameter count. Afterward, we propagate the extracted optical flow through a 3D ResNet 18 pre-trained on the Kinetics 400 activity recognition dataset to extract the spatio-temporal features of the optical flow. The output feature map is then average pulled over the spatial dimension to be prepared for the transformer encoder blocks. With a simpler and lighter approach, we just propagate the raw RGB frames through a similar pre-trained 3D ResNet that used in the previous approach to extract the spatio-temporal visual features of the sign language video, and then we average pool the output feature map to be fed to the transformer encoder blocks. As a result, we can merge the three approaches to build a multi-stream video understanding model shown in the video. Then we concatenate the outputs of the streams A, B, and C. The next step is to process the output using the transformer encoder blocks, which utilize the self-attention mechanism to extract the temporal information, then make a word classification using the classification layers. The experimental stage now is to try and test streams either solo or conjointly, and based on the results, we deploy the best performance model. That chosen model should not necessarily contain the three streams, however, it should contain the best combination of them. In the sentence level sign language translation subsystem, we use the same multi-stream architecture mentioned in the word level subsystem, except that we take the output of the transformer encoder block and feed it to a transformer decoder to build a language model that can generate sentences as a translation of a sign language video.
The objective is to deploy a model that converts the spoken language to a text, something that helps the deaf to communicate easily with the people in their life. We will use Vosk API as our automatic speech recognition model because it's a pre-trained open source ASR model that we can make modifications to it according to our task, its ability to work offline, and its lightweight to work on any system requirements. Also, it has an active community providing pre-trained ASR models for 17 languages, as training new ASR model would need more than a month and powerful GPU.
So after we have introduced our approaches, we will introduce our infrastructure that we will build our models on and deploy it to end user instead of depending on on-premises hardware that will be cost a lot and has problem with scaling and management. So we choose cloud option, Amazon SageMaker, where we can build, train, and deploy easily. Let's take a look what actually happening in background when we train our models in SageMaker. First of all training data should be located within an S3 bucket training and validation data. On the right side, we have EC2 containers which have our training code images containing our models. EC2 instance provides variety of computation options that help our project to scale up easily. When we start training, we get a copy of training code and the data from S3. Then we will able to train on model compute instances. Once the model is trained, we will freeze the weight of the network, and the model weight will be saved in S3 bucket as well. Then when we need to make inferences, we need to create an endpoint that will be connected to compute instance that will take inference code image and the weight that we produced earlier. Then the user is able to upload his video through the endpoint and get his translation easily. This is our web application that will be the user interface to upload user video that is required to be translated. And here this is a volunteering page to enable people who want to help us by providing more training data to make our models more accurate.
In conclusion, we try to build a two-way communication system that helps the deaf and the people around them. For that purpose, our system offers a sign language translation system that helps to easily understand the sign language of the deaf. The second system is an automatic speech recognizer that enables the deaf to understand the spoken language around them. By building these communication systems, we hope they will help the deaf to communicate more freely with the people around them and to make their lives a little bit easier, a little bit happier.